is actually a concept that you guys have continually tried to use in some of your daily questions. A couple of terms that have popped up in the daily questions that I've said, oh, we'll learn about that later. First one's momentum, and well, we'll learn about that later. But the other term that you guys keep using in definitions is power. Now, power actually has a very specific definition in physics, and that's the rate at which work is done. The rate at which work is done. Okay? Based on that definition, what would you place as an equation for power? Work divided by time. So power is work over time. Okay? Talking about units, that would be joules per second. Or we could go with a unit that we've developed, again, based off some old long-dead scientists, to specifically talk about power, one you're very familiar with, the watt. Okay. So if we wanted to calculate the specific power of some kind of object, we could do it based on how much energy it can use during a certain amount of time. So if we want to talk about, let's say, an object that can exert 500 newtons of force over a distance of 50 meters in a matter of 3 seconds, we could calculate what the power is that that object is putting out. Rather simply, it would be 25,000 over 3, and evidently I didn't bring a calculator over here today. Power of my calculator. So somebody who has my calculator, 25,000 over 3. Watts. To give you a bit of an idea, first question here, do I have anybody who's like automotively inclined in here? Like cars are your thing? No? Okay. Well, maybe a little? No? Okay. Sometimes I've got people in here who, like, as soon as I connect it to cars, they're like, oh, I get this. This is kind of my thing to talk about. Thank you. So I'm missing a 3, you're saying. Fixed? Okay. So if we wanted to put this into perspective for those people who are automotively inclined, we could talk about horsepower. Horsepower is, of course, just another way of talking about a unit for power. And depending on the type of power we're talking about, whether we're talking about an electric engine or a gas-powered engine, here's a weird thing about conversions. There is not one standard for horsepower. It actually depends on what kind of engine we're talking about. So gas-powered engines have a different conversion rate than certain other electric motors, which is really inconvenient for comparing the two. But roughly 762 watts is 1 horsepower, and I really congested all of that information. Why is it that value? Or why are they different for each one? I don't have a good answer for you. Yeah, no, I don't have a good answer for either. I did read at one point that this horsepower is roughly related to, it is an actual horse, but I can't remember what the breed or size was. Yeah, that's a good question too. How much power a horse can exert? Well, if we actually take the power equation and we take another look at it, power is, of course, work over time. There's another way to rephrase this. Since work is force times displacement, I can break down the work equation into force times displacement. And if I reassess how I group the variables, what can I calculate instead? Velocity. So I could say force times velocity. So the amount of force times the velocity at which it travels is power. which is actually really useful on one of the worksheet problems or practice problems that you'll find, I think, on today's assignment. Okay, so power, the rate at which work is done. A couple of different ways to calculate it. Recognition that roughly 762 watts is a horsepower. I can't remember which conversion rate that is, but I know it's one of them. And the last one I want to talk here. Anybody look at their parents' electric bill ever? Or your electric bill if for some reason you're paying the electricity at your house? No? Anybody know what they're charged for? Not how much they're charged. Kilowatt hours, not kilowatts per hour. Because that'd be a rate of acceleration of power usage. So we actually are charged for kilowatt hours. So this is on an electric bill. Kilowatt hours. So kilowatts, obviously just a rate of, or measure of power, and hours a measure of time. Well, if we take a look at our power equation, power equals work times time, and multiply by time, what are we actually being charged for when we pay our power bill? Work. We are being charged for the amount of work done to power your house. We're not being charged for a rate at which you're using the power. We're being charged specifically for how much work or how much energy is being used. Okay? So we also charge this in kilowatt hours rather than in joules because kilowatt hours are much smaller, or not much smaller. There are a lot of watts that go into a kilowatt hour. If we wanted to convert this, typically power's in watts. So we'd have 1 watt times, let's get rid of watts, or 1,000 watts to 1 kilowatt. And we're going to multiply by hours rather than seconds times 1 second, but we're going to convert that. 3,600 seconds to 1 hour. We're talking about 1 kilowatt hour is equal to 1,000 times 3,600, 3600,123 joule seconds. So rather than charging you for joule seconds, which would be the SI unit, and inflating the numbers by over 3 million times, we charge for kilowatt hours because we use a lot more power than joule seconds would be reasonable to state it in. Not enough. No, because that starts to branch into the chemistry of that, and I couldn't tell you how much energy you release based on burning a pound of coal. So that's really all there is to power. It's just understanding that it's the rate at which energy is used. It's what we use to state our electric bill, and it can be rearranged in a couple different ways. The most standard ways to measure power are in watts or kilowatts. Questions on power? Yeah.
Isn't there like a thing where there's something that uses W as a symbol and then like watts, it just watts?
Well, you mean like how work is a W?
Oh, yeah.
Yeah.
I know like there's like a unit that uses.
There is, but it's a unit used in quantum mechanics, if I remember correctly. So we don't have to worry about that. It's a, oh geez, I can't entirely recall. Yeah, you're right, there is one. It's WE something, I can't remember the rest, it's been too long. But it's in quantum mechanics, so we don't have to worry about it. Weber, yeah. Yeah, he's right. A Weber. What? Oh. All right. Um,